Harvard, did postdocs at Princeton, the Institute, I believe, and Harvard, and is now an assistant professor at UNC Chapel Hill. He's a string theorist. He's done a lot of work on string compactification, both for phenomenology and the more theoretical aspects. So,
okay, yeah.
Jonathan Heckman.
Okay, great. So first off, thanks very much for the chance to come and meet all of you and talk with you. So what I'm going to tell, and also for the chance to give a talk and tell you what I'm doing. So yeah, so this is going to be a talk connecting two topics. One is going to be connected with kind of a rather broad subject in the context of physics, which is effective field theories, and these govern quite a few physical systems of interest. And the other topic is going to be string compactification. And by that I mean what we're going to be doing is taking the famous fact that string theory appears to have more than 4 dimensions. It has extra dimensions. And what we're going to be doing, or what I'm going to explain, is how the geometry of those extra dimensions can affect the physics that's observed at long wavelengths. And really the interplay between this geometric part and this physics part is going to be what are we talking about? So a natural question is, what's string theory good for? And there are different answers depending on what you want to do with it. So one of the main selling points for a long time about string theory is that it provides a way of at least self-consistently talking about some quantum aspects of gravity. There's also kind of been more recent developments connected with one of these other topics, namely possible connections to particle physics, strongly coupled systems, and just the mathematical structures are incredibly rich that come out of this. So I'm not really going to talk about the first one, quantum gravity. I'm going to talk about rather kind of the new developments connected with using strings as a way of understanding these things, in particular this one here. So what this talk is going to be about is taking the geometry of these extra dimensions and connecting it with effective field theories. And don't worry, I'll explain what each of those things is supposed to mean. And kind of the goals in this program are kind of on the short term. The idea is to take the classical geometry associated to those extra dimensions and use it to start squeezing out effective field theories. And kind of an open question is still, we know how to do this in lots of examples, but kind of what the rules of the game are in all possible situations have kind of yet to be filled out. So this is kind of a short-term thing that needs to be done. And then once you've got those geometries telling you about effective field theories, what are the possible kind of physical states, what are the properties, what are the structures that you get? So it's not good enough to just say, oh, you got an effective field theory. What kind of effective field theory? What's going on in that theory? And then more broadly, kind of putting quantum corrections into the classical geometry. And this leads into much more conceptual questions, which, in my opinion, haven't really been addressed kind of adequately in the context of string theory, but there's certainly things that have to be done at some point. Things connected with what happens when this classical geometry is allowed to fluctuate. Typically what you'll get is the effective field theory coupled then to quantum gravity, and this enters into a lot of much more kind of deeper terrain. So for this talk, I'm basically going to focus on some of these short-term things, and in particular kind of classical geometry and how it connects to effective field theories. So let me tell you, at least in a couple slides, what each of these things is. So what's an effective field theory? It's an incredibly useful tool for understanding quantum dynamics associated with a lot of systems. And in kind of just a couple lines, what it tells you about is it allows you to kind of organize your ignorance about a lot of systems, basically saying, well, there's some high energy behavior of the system, but what we're going to do is kind of focus on kind of the long wavelength, low energy dynamics. And what we're going to do is remain agnostic about what happens up near the so-called cutoff. And the cool thing about this is that it describes a lot of physical systems. So what's an example of a physical system that does that? Water. So short distance description you can think of as being about water and little tiny molecules, but if you start looking at very long distances, probably don't care too much about the details of it looks like this kind of object. Maybe you just care more about these like tidal waves, things like that. So that's an example of kind of a long distance description, and it'd be kind of insane to say I only want to talk about kind of the short distance description. Now, once you play this game about, oh, I can start going to shorter distances, you can also ask what's going on inside of a water molecule. And for example, inside of this, there's clouds of electrons around each of these atoms, and there's a nucleus, for example. So you can ask what's going on in there. And that's another effective field theory, or at least part of it, which is the standard model. So this thing is pretty good at describing lots of subatomic processes. This is the thing that was found recently, Higgs boson. So this is, so for example, these are the force carriers, and then everything we know about these guys interact with one another by exchanging these kind of force carriers. Okay, so this is another example of an effective field theory from this perspective, because it works great when you're way below the scale where quantum gravity can hit you. So this is another great way of organizing kind of your ignorance about what's going on at like very high energy scales. It works great at these low energies. And kind of an old idea, which is still very much in play, is to kind of ask if we start going to those higher energies, so-called 1019 GeV or so, then you might imagine completing this via some other system that includes quantum gravitational effects. And an old proposal, which is still very much in play, is to complete it via string theory. And that's kind of a thing I worked a lot on my PhD thesis, but it's not actually what I'm going to talk about too much today. Rather, I'm going to talk about some other examples of effective field theories, namely so-called conformal field theories. So these are theories which are pretty neat from both a theoretical and from many standpoints. And what they involve is, roughly speaking, theories where even if you specify kind of short distance behavior, once you get down to long distances, all the details about those energy scales start washing away. And so you're left with a system that really only kind of depends on the angles and no longer about, say, this has a particular mass. Everything is basically massless at this point. And it describes a lot of physical systems. So in particular, dynamics associated with certain phase transitions. A famous example in the context of quantum gravity is the connection between these conformal field theories on the one hand and certain aspects of quantum gravity connected with spacetimes that have, say, a negative cosmological constant. So the opposite of kind of what we see around us, positive cosmological constant. And also kind of more the fact that if you take one of these field theories and put it on a spacetime, not all the details of that spacetime matter, in particular not the distances between them, but rather just the angles or the conformal geometry. So those are some examples of effective field theories, and the other half of this talk is going to be about extra dimensions. In particular, the extra dimensions that come out of something like string theory. Okay, so even after 40 years, I think it's fair to say that a completely sharp definition of what string theory is has yet to be found. What we do know, however, is various clues as to how it's supposed to fit together. And one use along those lines is to use it to study quantum gravity. And the idea here, a very old idea at this point, is that you have a quantum of gravity, a graviton so-called, and the idea is that it extends out into a kind of closed loop, a closed string. So that's one application. The more recent application that's kind of been picking up a lot of momentum in recent years in particular is to use it as a way of studying quantum field theories or effective field theories. So the idea here is to really kind of turn things around and not say something like, oh, quantum field theory is old hat and everybody knows how it works. The idea is really to use the lessons we've learned about string theory as a way of understanding things connected with these effective field theories. And two notable examples of this are context of ADS-CFT. Basically, you can start making interesting statements about strongly coupled field theories using a gravitational system. That's one option. And another option is to basically take the geometry of the extra dimensions and convert it into questions about effective field theory. So it's really the second one that I'm going to focus on. So how do you get an effective field theory from something like a string compactification? Well, one thing you can do is you can use this kind of famous fact, or embarrassing fact, depending on your point of view, that string theory predicts that you typically have more than 4 spacetime dimensions. So you can have 10. So the 4D effective theory, or the 6-dimensional effective theory, or the D-dimensional effective theory, is controlled by taking that number to be big, so this is Minkowski space, in say 3 plus 1 dimensions, or say 5 plus 1 dimensions, and taking the other dimensions to be rather small. So in other words, this is kind of the short distance cutoff aspect of it. Namely, once we go to short distances, you can ask what sort of effective theory do you get left over. So if we wanted to talk about a 4D theory, we have 6 small extra dimensions. If we wanted to talk about a 6-dimensional effective theory, we have 4 small extra dimensions. And so you can obviously play some game where you partition these, or you make various geometric constructions like that. So this is just part of the game of like trying to construct an effective field theory. The geometry that's happening in these internal directions is going to control what's going on in the big dimensions. Okay, so that's one of the ingredients. And that was it's basically just forced from self-consistency of trying to write down a proper theory of strings. I mean, it's not like you have a choice in the matter. Okay, what's another thing that's forced on you by self-consistency? That some of these strings get to end on other dynamical objects. And these things are called, for example, p-branes. So p here stands for the number of spatial directions that you have. So here are some examples of what p-branes look like. I'm picking 6 dimensions, by the way, because that's where I'm going to be heading. So you might say, why is he talking about 6 and not 4? I'm going to be focusing on 6D theories, so that's why I'm picking this dimension. So in this case, if you had 4 small extra dimensions, a one brane, or say a string, would be something that kind of moves forward in time and has one spatial direction. And you could also have effective strings, things that are really kind of higher dimensional objects, but you don't discover them until you get to really tiny distances. So here's an example of an effective string, which is really a 3 brane. So we can count up. There's 1 temporal, and then there's 1, 2, 3. So there's some 3 spatial directions. So if we look, however, in the 6-dimensional spacetime, we forget about what's happening here, and we see only 2 directions. So it looks like an effective string from the perspective of a low-energy observer. And here's an example of a 7 brane. Again, this is just counting from 1 to 7. So these x's here just tell you which directions are being filled. Okay, so those are the ingredients that kind of go into, say, a string compactification. There's the geometry of the extra dimensions, and then there's kind of the branes that can wrap various directions in those extra dimensions. And putting these things together starts to generate interesting effective field theories. So at this point, I think it's fair to say, since the 90s, that there have been a huge number of different types of effective field theories that people have concocted using string compactification. So I don't have the time, and I don't think you have the patience for me to go through all the different ones. So what I'm going to do is I'm just going to pick a particularly what I consider cool example of this, and just explain why they're interesting and what you can do using string compactification to understand what's going on in these theories. And the ones I'm going to focus on are what sound very exotic, 6-dimensional superconformal field theories. So I'll tell you what these things are, and then how you can use string theory to understand what's going on in these guys. So what's a 6D CFT, or SCFT? First off, what's a 6D CFT? It's one of these things that doesn't have any energy scales or distances, but just has kind of angles going between things. So what are the symmetries here? Basically, you just take the usual Lorentz symmetries, the ones that rotate space and time, plus a few extras, mainly associated with, say, scaling and translations. Okay, so what's a SCFT? It's a CFT that has supersymmetry. And the reason why supersymmetry turns out to be useful here is not for any phenomenological or particle physics motivation here, but rather just because it provides kind of technical control over what's going on in the physical system. Without supersymmetry here, it becomes rather challenging to write down anything that you can reliably state. So you can think about this as just adding some additional symmetries, some additional constraints on top of the ones you already had. And roughly speaking, you can think of the q's as giving you, say, a square root of a momentum. And in the context of making something that's like a 6D CFT, you got 2 options, basically. One is that these q's, you have 8 of them, and one is that you have 16 of them. And basically, you count them in multiples of 8. So the ones with the minimal amount of supersymmetry are what are called the 1, 0. And as you can imagine, if you double that, you get the so-called 2, 0 things. So I'll be explaining what these things kind of look like from the perspective of string compactification and what we kind of know about them using that geometric perspective. So these are going to be the two main classes of theories. So why would you want to study these theories at all? What's so interesting about them? Well, for a long time, nobody thought they existed. And I think that's a pretty interesting reason to study them, because for a long time, there was zero evidence that these things could be written down. And basically using all the techniques that were kind of developed about quantum field theory, starting from basically its inception up through modern times, up through, say, the 90s, just couldn't write down any kind of way of convincingly arguing that these things actually existed. Moreover, 6 turns out to be the maximum dimension in which you could potentially have it. So there's a famous result from Werner Nahm back in the 1970s that it could have been the case that there could have been a CFT. And that was in the 1970s, but he didn't have like a way of exhibiting that these things actually did exist. Now, the last reason why these things are, I think, pretty conceptually exciting is that they kind of counter the usual intuition we have about how to build up a quantum field theory, which is we usually have intuition about things being built from particles. And we talk about quantum field theory providing us a way of talking about particles and combining that with relativistic dynamics. These things don't involve particles. They really involve kind of extended objects like strings. And the strings here are not really going to be the superstrings or superstring theory, but rather some effective strings that are going to be coming out of it. So this is pretty conceptually different from kind of the terrain we're used to in like 4 dimensions. Namely, these things are showing up in involving strings, and tensionless strings in particular. So just as a picture, here's what I mean by a string. It fills one time in one space. And a particle we think of usually as having some kind of mass. A string is going to have, say, a mass per unit length, or a tension. And the case of an SCFT is going to be one where that basic energy scale, that basic distance scale, gets washed away. So in other words, we're going to be talking about a string that is very long and floppy, so it has no tension. Okay, so this is a pretty hard thing to study and understand the quantum dynamics of. So it's very hard to say, write down a Lagrangian, quantize it, and say what is going on in the system. So it's conceptually challenging. So, for example, the force carriers here we're used to from particle physics usually involve, say, exchange of vector bosons, say an electron interacting with, say, a photon, quantum of light. In the case of these string theories, these effective string theories, they don't really involve vector bosons anymore. Rather, they involve this kind of generalization of a vector boson, a kind of two-form potential, or a tensor boson. And this is where all the complication starts, basically by adding this extra vector index on top of the system. It becomes incredibly challenging to actually write down a quantum theory that has this kind of stuff floating around. And from a more conceptual point of view, this is actually pretty important to kind of straighten out because, if you talk to guys over in the math department, they get frustrated whenever a physicist says, "Oh yeah, we know what a quantum field theory is," because a completely satisfactory definition of what a quantum field theory is still not completely available. And I think it might be premature to give a definition, but what we can certainly do is kind of provide examples of the kinds of things that we expect a quantum field theory to look like. And this is one of those things that kind of challenges some of the previous notions of what it means to be talking about a field theory at all. Okay, so what are some other reasons to study these things? Well, it's not a completely practical reason. You're not going to see this, but it provides a lot of conceptual input into other formal objects of interest. So, for example, if you take these 60 theories and you compactify further, namely imagine that two of the dimensions are quite tiny, that's what this means, then it allows you to solve strongly coupled dynamics involving electrons and monopoles, magnetic monopoles, in lower dimensional systems, in four-dimensional theories. So, for example, you'll have, say, Gauss's law, and you'll have some monopoles here. And basically, the electrons and monopoles just correspond to taking those strings we were talking about and wrapping them around different cycles of the extra dimension. So, for example, if you wrap something around, say, this cycle, you get an electron. This cycle, you get a monopole. Okay, so those are some examples of ways that the 60 theory can show up. It's both conceptually exciting because it kind of challenges what you mean by a quantum field theory in the first place. And on the other hand, it provides kind of insight into a lot of four-dimensional systems that are kind of tricky to understand just in straightforward Lagrangian, using the quantization of the Lagrangian, which is kind of the standard toolkit that a lot of people, certainly I, grew up learning. Okay, so what are we going to do in this talk? We're going to talk about what 60 CFTs look like. And so before I get to kind of the string theory side of it, I'm going to ask from the perspective of, say, just being a low-energy effective field theorist, what could we say about the way that these things look? And we're going to encounter a roadblock in trying to understand kind of the theoretical structure that goes into them. And this is where string theory is going to come in and provide us with some additional insight into how to build these things up. So what's the bottom-up perspective on these guys? Here it is. You draw a picture. So this thing is what I'll call a Quiver diagram, or it's a moose if you're doing particle physics, and which each of these things tells you is quite a bit of data about the kind of quantum field that we're talking about. So let me fill it in. This is what this thing tells you in 6 dimensions. Each of these circles corresponds to kind of a generalization of the photon or something like a gluon. So you can think about the force carriers as filling out, say, n by n matrices. That's what each of these circles corresponds to, these force carriers. And then these things here, these sides, these links going between it, are kind of like the analog of the electrons, or say quarks, saying that they interact with the force carriers that are given down. So in pictures, what's going on is you have your force carrier here, that's associated with that circle, and then it, say, bounces off that generalization of an electron. And so if we wanted, say, electrons interacting with one another, they could exchange these kinds of gauge bosons. Now, in the context of 6 dimensions, it turns out that in addition to these guys, you've got some other guys, those pesky two-form potentials, which are kind of coupling to the strings. And one of the ways they'll show up in your effective field theory is in terms of some additional interaction. So, for example, 2 of the force carriers interacting with yet another force carrier. So this is where things start to get a little hairy to describe, because you've got to deal with these guys and also these guys. And by the way, these two-form potentials are also associated with the circles here. These square things, by the way, can be thought of as kind of non-dynamical non-dynamical vector bosons. So they're kind of what are called flavor symmetries. But all of these things are kind of dictated by kind of quantum consistency of the 6D theory. Things that an effective field theorist can certainly spot. Things called just making an anomaly cancellation forces, particular values for the sizes of these matrices of force carriers. Okay, so this is to make just an effective field theory in 6 dimensions. Now, how do you make an SCFT? How do you argue that this thing is going to be a theory that doesn't have any energy scales and just is completely free of that kind of stuff? Well, it turns out that in order to do that, you need to ramp up the strength of the coupling constants in the theory. So in other words, you need to have not just like one little interaction between, say, your generalization of an electron and a photon, but you need to have lots and lots of them happening, so there's all these quantum processes going on. And it turns out that that limit, that coupling constant there, controls the tension of the string in the effective field theory. The limit where this, because the coupling constant turns out to have it turns out to be dimensionful in 6 dimensions. This coupling constant controls the tension of the string, and in order to get something that has these tensionless strings, the guys that are really driving the show in a conformal field theory, you need to take the tension to 0 size, which in turn ramps up the coupling constant. It makes things very, very strongly interacting. So when you do all of that, it's not really clear that you know what you're doing. So this is one of the reasons why nobody thought you could write anything down. Basically, any time when you try and write down a kind of description like this, the place that is kind of most interesting from a theoretical standpoint is precisely the place where you have 0 theoretical control. So there's no real good evidence that you can describe the quantum dynamics of this thing. And so therefore, how do you even know that there's anything interesting happening there at all? You could just say, your approximation broke down. I don't believe a word you said about SCFT this or that. So what I'm going to be telling you about is kind of the extra dimensional perspective on these things, which provides kind of a complementary viewpoint to this, and actually allows you to say, yes, I expect there to be some kind of SCFT getting generated precisely at this point. And it's not going to involve anything to do with, say, Lagrangians or anything like that, which is kind of the standard trick a lot of energy theorists will use in these situations. Okay, so that's kind of the bottom-up perspective, and that's where it kind of the wheels start coming off. Let's now go to the stringy description. Okay, so I keep telling you I need tensionless strings. Why don't I just use superstrings? It turns out that those guys always have tension. And so they're not really suitable for the thing we're trying to talk about, which is a limit where all the distance scales or all the energy scales start washing away. So we're not going to use the standard superstrings that are commonplace in superstring theory. What we're going to do instead is build our strings from effective objects. So in other words, there's going to be some short distance behavior where this thing is described in terms of not really a string, but a higher dimensional object, a so-called 3-brane. Remember, that's something that fills, say, 3 spatial directions. We're going to use this 3-brane to build an effective string in the 6-dimensional spacetime. So we'll have the one temporal and one spatial direction. And then the tension of that string, namely the mass per unit length, turns out to be controlled by how big the cycle is that we're wrapping that 3-brane over. So the bigger we make that cycle, the bigger the tension is. So you can work out that the tension of that effective string is controlled by the volume of that thing. So in the limit where that volume squeezes down to 0 size, the tension of that effective string drops to 0. So that's going to be the limit we're going to be interested in. We're going to be looking for a theory that involves these tensionless strings, namely the limit where these things are squeezing down to 0 size.
Still you start to speak, say. Still you are starting to speak, say.
Yes, yes. So the 3-branes are part of the internal consistent pieces of it. So I'm starting from string theory, and I'm going to use it to generate the 6-dimensional theory. Yeah. Okay, so what's the name of the game going to be? I'm going to try to find 2 cycles in my 4 extra dimensions and squeeze them to 0 size. So the 3-brane is going to wrap over this thing. That's what this line is supposed to represent. So that circle is supposed to represent 4 dimensions, and this red line is supposed to represent 2 dimensions. We're going to squeeze that to 0 size. That's what this thing means. Squeeze it to 0 size, and in that limit, the 3-brane that was wrapping it is going to turn into a tensionless string. So there's some interesting physics already, just talking about the geometry of just that guy by itself, which is that if you look at the self-intersection of that guy, in the low, what it tells you in the low energy theory, so if you imagine shaking this thing around in some way, it actually tells you what the charge of that thing is. So just like you want to read off, say, the charge of the electron or, say, the magnetic charge of the monopole, self-intersection of this thing in the extra dimensions tells you that string charge. By the way, this is always an integer. Okay, so Great, so that's an example. So let's now talk about some special classes of these six-dimensional CFTs, particularly the so-called 2, 0 theories. So these are theories that have lots of constraints on them. So these are kind of, it's like the maximal amount of supersymmetry, and so you might imagine that things are pretty heavily constrained. And it turns out that when you do that, the self-intersection of all these guys is forced to be -2. And a priori, you can have more than one of these 2 cycles collapsing at the same time. If you have more than one 2-cycle collapsing, it means that you'll get a different spectrum of strings in the 6-dimensional effective theory, and therefore a different type of 6-dimensional conformal field theory left over. So here's an example of one with one 2-cycle. That's what this blue blob corresponds to. And if you have 2 of them next to each other, which intersect once, you'll get one theory. And if you have 3 of them, you'll get 3 different string charges. Okay. So how do you make a CFT? Well, we might as well introduce some kind of way of cataloging what we mean by those different intersections. So you can introduce an adjacency matrix or an intersection pairing for the different 2 cycles you have. So let's make an adjacency matrix like this. And basically the CFT condition is that you have to be able to squeeze all these guys to 0 at the same time. That you have to have a parametric limit where you can take all of them to 0 simultaneously. That's the meaning they have that these tensionless strings are all part of the same theory in the first place. So that turns out to be the condition that this matrix that we're writing down is positive definite. And moreover, it turns out that these things can only intersect either once or no times. And it turns out that these things have been classified. So the theories with 2, 0 supersymmetry, we kind of already know all the different ways you could write down such a theory. So who did that? Was this string theorists? No.
How do you define the intersection here? Is it the one-dimensional intersection?
So it's happening at a point. So what's happening is if we look at, so let me draw the extra dimensions. Where did they go from? 6, 7, 8, 9. So one of your guys is going to fill out, so this will be one of the signals. It'll fill out the 6, 7 directions. The other guy is going to fill out the 8, 9 directions. So the intersection is actually going to happen at a point. And because it's happening at a point, we get to talk about it in terms of just count the number of points where these things happen. Yeah, so that'll be like signal prime. And now the neat thing is that when you start building these more complicated geometries, you'll have, okay, it gets harder for me to draw it, but one thing you'll have is like a chain like, so this is a pretty common picture, where each one of these lines corresponds to a CP1, and each one of these things where 2 of the lines meet is one of those intersection points. So for example, the adjacency matrix for, say, 2 of those guys next to each other will look like -2, -2, and then 1 and 1. So it'll be like this. So there's one intersection point. And it's a symmetric thing, because I can intersect A with B or B with A. And so it doesn't matter which way I pick it. All right, so that's the name of the game. We're going to try and find all the guys that have basically 2's on the diagonal, or -2's on the diagonal, and 2's on the diagonal, and then some 0's or 1's off the diagonal. All right, so that's already been classified, it turns out. And some friendly mathematicians did it for us. They did it a long time before anybody was talking about 2, 0 theories. This is a famous result on classifying kind of the simple algebras. This is summarized with so-called Dinkin diagrams. Basically, if you try and write down one of these positive definite adjacency matrices, this is the full list of things you can do. And what these things are telling you is you got the 2's on the diagonal, and then if you have one of these blobs intersecting the other one, that means put a 1 on that entry of that big matrix. Okay, so it's called an ADE classification.
So how come you only get simply laced? Is there something?
It's because the diagonals are -2.
But is there a role for the B and C series? Or?
Yes. So if you go down in dimensions, you can generate the other ones. So if you go down to say 5 dimensions or 4 dimensions, what will happen is, so for example, in this case, there's kind of a Z2 symmetry or reflection symmetry, and if you go down in dimension, you can then twist the theory by that, and going down, you'll generate, for example, the F4. Yeah, and then by a similar token, if you take the A series, sometimes you'll have a reflection symmetry across if it has the right value of n. That reflection symmetry will allow you to generate, for example, the SP type algebras. And if you take the Ds, then you'll get the SO odd ones. So those things happen, but they don't happen in 6 dimensions for the 2, 0 theories. Okay, so those are the 2, 0 theories. That's great. Now, a natural question you can ask is, okay, that was the case that had kind of the maximal supersymmetry, namely the maximal number of constraints. Can you say anything about what happens when you have less supersymmetry? Namely, if you start relaxing the conditions, you might imagine like, things break loose and become much more complicated. How complicated does it get? And can we say what all these things look like? In other words, are the 2, 0 theories kind of a special thing, or do they fit into a bigger picture about what a 6D superconformal field theory is supposed to look like? Okay, so this topic was discussed by many groups for a while. Basically after this, okay, so basically here historically, ADS-CFT happened and people abandoned this and they stopped working on it for a very long time. So what happened though is I think people, well, anyway, I picked it up again with my friends back in 2013, and what I'm going to tell you about is kind of the recent developments about kind of filling out the picture about the way that these 1, 0 theories look. So, how do you build 6D CFTs? What I'm going to be telling you about is kind of a trick for building them. It's a technical tool using a thing called F-theory. And this is going to turn out to be a really useful way to start building up more general kinds of string compactifications. Okay, so there's a hidden assumption what I told you about so far about the kinds of geometries I was looking at. There were ones where if you look at the Einstein field equations for the 4-dimensional extra dimensions, it turns out that they're Ricci flat. And by that I mean there's no local source for stress energy. And that in turn limits the kinds of strings that you can stick into the system. So it always requires, in other words, the self-intersection of these guys turns out to be -2. Okay, so you might ask, how come I'm only talking about things with -2? Why don't I talk about -1, -5, -20, that kind of stuff? Am I really that limited in the kind of string charges I can write down? So more generally, there are other ways of building up solutions here where the 4 extra dimensions are not Ricci flat. And in order to satisfy Einstein field equations, you then have to start switching on so-called sources for stress energy, things called fluxes. This allows you to think about situations where the string charges switch away from being 2 and could be something more general. So what does F-theory do? It's basically a machine for systematically solving this equation. That's all it does. It's just like a trick for doing it. What is that trick?
Still restricted to integers?
Yeah. And from an effective field theory standpoint, that's what you should have expected because of Dirac quantization, or the analog of Dirac quantization. The thing that's going to get shifted a little bit is kind of what values of the integers. But yeah, so we're going to see like what the upper bound is, or whether there is an upper bound. Okay, so how do you solve Einstein's field equation with these sources? Well, you don't really completely solve it. You basically just give an existence proof that this thing could have existed. And it turns out this is really conveniently captured by not working just with the 4-dimensional spacetime, but over each point of that 4D spacetime, decorating by a 2-torus, or a donut. And you can write down a corresponding 6-dimensional spacetime. The 2 extra dimensions are coming from this T2. And the sources just correspond to special places where that T2 starts squeezing off in some funny way. So there's a singularity happening here, and that singularity is encoded in the physics, saying, ah yes, there's a physical source there. And the whole thing is encoded in this 6-dimensional geometry. Now, the condition in order to find a kind of self-consistent solution to the equations of motion is that this 6-dimensional thing has to be flat, Ricci flat, not the 4-dimensional spacetime. So the name of the game is to find 6-dimensional geometries with this particular fibration structure, a T2 fibered over a 4 manifold, such that the whole thing is Ricci flat. So in more fancy terms, this is an elliptically fibered Calabi-Yau. Okay, so that's all we're really going to need about F-theory. Namely, we're going to be saying, we can look for places where the T2 pinches. Okay, so F-theory has found a lot of applications. Here's some of them.
Just one quick.
Yeah.
You have to add 2 space. You can't do 1 space 1 time.
No, if you add 1 space 1 time, technically speaking, the effective field theory is no longer in Minkowski's signature. It's now in Euclidean signature. So this is a game people have played where you kind of ask about Euclidean signature things, and then you get a Lorentzian T2. But from my perspective, where I want to have a CFT in Minkowski space, I'm going to be restricted to 2 space. Yeah. Okay, so F-theory turns out to be a useful thing. You can build particle physics models. So for example, you can make models of neutrino physics with the right values of the mixing angle. You can also build fun particles. These are F-theory unparticle scenarios. You can also build CFTs, and that's what I'm going to talk about here. Okay, so here's the setup. Here are the sources, and basically the types of ways you can pinch it off tell you about different types of objects that are getting added to your system, kind of automatically, just in order to make a self-consistent geometry. So you pinch it off in some way, and it turns out that if you look at where this thing is happening, it's happening at basically some location in the 8, 9 directions, but it's kind of filling out the 6, 7 directions. So you might as well call it a 7 brane. It's just by dimension counting. That's it. But then if you actually look closer, you find that, oh, this thing actually has some gauge theory dynamics associated with it. And you can see, yes, there's this, the volume of the 6, 7 controls the value of the gauge coupling in the 6-dimensional dynamics. All right, that's great. So what kind of pinching off can you get? So actually, this was classified, again, by mathematicians, and then it was picked up a little bit later by kind of these guys, who I would consider hybrids between physics and math. And what they did is they found that, okay, if we now start modifying that self-intersection number, the charge of that string, we can ask what happens to the corresponding behavior of that T2. And what they found is that this thing actually is always pinching off when this charge is high enough. Physically, that kind of makes sense, because when the charge is high enough, there's more mass, or there's more energy associated to it. The more energy associated to it, the more you should expect this thing to be pinching off. And indeed, as you start going up in charge, you can see that there's more and more things pinching off in this T2, until you hit this kind of upper bound. And beyond this point, this geometry gets so singular that you can't even solve the equations. So in physics terms, what's happening is you hit E8, and that's kind of the biggest simple gauge group factor you can write down. And beyond that point, there's just nothing available. So that means that when you start writing down the spectrum of strings, they're basically limited to be between 1 and 12. Okay, so
you're drawing extended Dinkin diagrams now?
yes, so they're actually the affine Dinkin diagrams, because what happens is, because it's a T2, it has some kind of loopy structure. So that's what's happening, for example, in this case here. Yeah. Okay. So let me go back now to the case we already talked about, the 2, 0 theories. We can still write down our Quiver diagram, our picture. Each of these things corresponds to a 2 cycle, which is pinching off, and that gives us a corresponding string. And that just means that we have our effective string generated by a 3 brane, wrapping these extra dimensions. Those guys squeeze to 0 size, and produces the tensionless string. When you start allowing this pinching off, you start generating more kinds of CFTs. So here's an example of something you can do. You can take SU5 here, and that corresponds to a very specific choice of pinching off that T2. This could have been SU6, SU7, SU8. I just picked an example. And the thing that's happening here is you have now, in addition to these 3 branes, these 7 branes. That's what this pinching off tells you. And you play this game by asking, okay, what other kinds of pinching off could occur? Here's another example of the pinching off that can occur. So here I've drawn what that diagram looks like, and you basically put E8 factors here. Okay, but what does this mean? This is a little bit puzzling to anybody who's played with Quiver diagrams in the context of Lagrangian field theories, because remember, initially I was telling you that these things corresponded to particles. Now it's a little bit weird. I haven't seen anybody really talking about this thing being described in terms of particles before. And it turns out these things are not really particles in their own right. They turn out to be much more kind of rich physical objects. They're not like electrons anymore. They're themselves kind of interesting geometries associated with this. So in other words, what happens is that the links aren't particles anymore. Instead, they're SCFTs themselves. So here's what happens, for example, in the case of 2 E8s next to each other. You go through the process of building up that 6-dimensional geometry, and what you find is that at that collision point between the 2 E8-7 branes, there's more stuff hiding in the geometry. So you resolve that singularity, you find some additional structure in there, and you get a very specific pattern of the string charges that are associated. So there's something like 11 additional 2 cycles that are just part of the story. So all these things are kind of just algorithmically popping out of that procedure. Namely, here are the string charges that you get. Okay, so this is an example of how you would start building kind of more general types of CFTs. You would have these kind of collisions, and you'd have some stuff going in between them. And this is all kind of like dictated by the geometry of this F-theory compactification. It's not like it's not a very loose object at all. It's pretty much just forced on us by the equations of motion. Okay, so what I told you about is how to build a few CFTs. Namely, you draw a picture, and you start looking at different ways of pinching off that T2. And you might ask, can you build all of them? So what I'm going to tell you about now is basically all the different ways of building 6D CFTs. So not just one of them, but every single possible one you could ever think of. So, by the way, this would be an insane thing to try to do for a lower dimensional system where it's still pretty much a very loose thing, like write down every possible Lagrangian. Good luck. You know, it's a pretty wild topic. Here it's going to turn out to be rigid enough that we're going to be able to get somewhere and say, this is the only way to build things. Okay, so this turns out to be a geometry question. We just have to classify all the 6D geometries that you can write down. So what I'm going to tell you about is how you do it. What you want to do first off is you want to find all the different choices of those four extra dimensions, such that you could put down, say, some set of strings in the first place, things that could support a CFT. Then we're going to look for all the possible ways of taking that T2 fibration data, those two extra dimensions that F theory wants us to add, and find all the different ways of pinching it off. So the combination of those two is going to cover every single possible way of building an SCFT in this setup. So what's the first punchline? There really is a generalization of that Dinkin diagram thing I was telling you about. And this is a priori totally unclear that this would happen. It could have been that you get incredibly wild-looking, complicated trees and so on. But it turns out that, it's constrained enough that you can really pin it down. So this thing looks like, again, those pictures I was drawing. And there's just a little bit of extra stuff happening, and some little tiny amount of decoration at the end. Punchline number 2 is that everything gets built out of little tiny building blocks, namely those little 2 cycles. And basically all the different ways of gluing them together. So you've got your atoms, if you like, and you've got the ways of binding them together to make bigger structures, bigger molecules. So radicals. And here, for example, is like one of these sequences of integers, and they get more complicated as you go to the 8 and the 8, and so on.
The diagrams in the previous slide have a name somewhere
These things?
in some math place.
Not as far as I know. The other thing I should point out is that if you don't impose the elliptic fibration condition, you say, I want to classify all positive definite adjacency matrices purely for the base. As far as I know, this is still an open problem, and it's not totally clear like what you would write. So we're getting some mileage from also imposing that elliptic fibration constraint, namely all the possible ways of self-consistently solving the Einstein field equations. If we didn't impose that, the problem gets a little too loose, and you can't do anything. So I don't know if there's a special math name. I was calling them generalized quivers. Okay, so here are the building blocks. The charges run from 1 to 12, and then there's a few extra structures. These are the things that were written down in a paper by Dave Morrison and Wally Taylor. Kind of the basic glue which holds everybody together is the single unit charge string. That's a guy I actually didn't talk about too much in the context of the 2,0 theories. You might ask, why did you start at charge 2? Why didn't you start at charge 1? I thought you're supposed to start at the bottom and work your way up. Well, this is where this guy lives, and he turns out to be rather interesting by himself. Turns out that we know that this thing has an E8 flavor symmetry. This is, again, predicted by the F-theory geometry, and that means that all the physical states of the system basically transform according to multiplets, or irreps, of irreducible representations of E8. Building up more complicated geometries just involves taking those blocks and sticking these -1 curves in between them. And there's a gluing rule that goes along with it. Namely, basically you have to ask, are you gauging a flavor symmetry appropriately? So you start with the 8, you ask, can you gauge some subalgebra of it? And that tells you whether you can start piecing these things together. So here's kind of a fancy example of gluing. We got these -1 curves, and in between are these blocks. Okay? So
once again, you say this structure is fixed. And by what again? I know you said it, but I've lost.
Yeah, so I didn't really explain it that much. So basically what happens is you have these two E8s meeting. And what happens at that point where they meet is that you find that the geometry is too singular to satisfy the Ricci flatness condition for the whole 6-dimensional system. So you perform an operation known as blowing up to kind of repair that geometry. You cut out that point and you put in some extra 2 cycles. And the self-intersection of those additional 2 cycles is that's the thing that's being dictated by this collision. So it turns out that you have to do 11 blow-ups in the base. And then that's why I say, there's 11 additional strings that come out. And moreover, when you do that blow-up, the self-intersection of those new guys that you keep adding is completely forced by that process of iteratively building it up. So that's why I say I have no choice with these string charges. It's not like I can say, I'd like to change this from 5 to 6. I can't do it. It's just kind of forced that way. So here's an example of the gluing. We put those -1 curves in between. So you can put this together, and you can ask what kind of topologies for these things. And it still looks pretty wild. Basically, you get a structure where it says, all right, you can't have any closed loops. You can have these kind of fancy-looking trees. And you have to write down the analog of this adjacency matrix condition, namely that adjacency matrix for this now bigger thing has to still be a positive definite. But, you can write down lots of trees. I could have written down more complicated trees. What's to stop me from writing down an arbitrarily complicated tree? It turns out that this positive definiteness condition is about to kill off most of that structure. So to kind of explain the resulting structure that you get, it's helpful to split those guys up, the string charges, according to the fiber type. So this thing here just corresponds to the kind of pinching off that's going on. So you can split them according to whether they have a DE type algebra, SO8 or E6, or a non-DE, so that's basically everybody else. So these guys are, roughly speaking, like the radicals, the things that kind of glue together the atoms. And these things are more like the atoms, namely the things that are going to get placed together. So then, another nice piece of terminology. At this point, this is just notation, so it turns out to be nice notation for the classification purpose. Is to split them further. Namely, if you have DE-type curves, put them here. And if you have things going in between the DE-type curves, put them like that. So here's an example of where this notation comes up. We already did this in the context of that picture. So instead of writing down this kind of crazy thing with 11 curves, I'm going to be lazy. I don't want to write that. I'm just going to draw a line. This is identical information. Okay? So the first point is that, this looks like it's simplifying my task in terms of just trying to write down all the possible structures you could write. Okay, now the big surprise when you do this is that you then start asking about what kind of diagrams you can put together, subject to the condition that this thing is a positive definite adjacency matrix. And it turns out they have a pretty simple structure. They look like this. Basically what happens is every time you try to add another node up like this, or start trying to make a tree, you find that this positivity condition, namely that you can get tensionless strings at all, is violated. So I can explain that in a little more detail probably after the talk, but that's basically what you find. And moreover, you find these kind of interesting stability conditions on the actual gauge groups you get. So they obey this kind of nested relation, so that basically the biggest gauge groups sit in the middle. And physically, that's kind of like saying, the biggest center of mass sits at the middle of the thing, and it gets weaker and lighter as it goes out. Okay. So what did we do? Classified all the sequences of these G's you could write. So this just involved Mathematica scripts, basically. Classified all the different ways of sticking kind of links on the ends here, and also links here. Turns out that all the links here are just basically forced by this kind of minimal blow-up procedure. But there's a little bit more freedom that happens near the ends. We're classifying all that too. And all the possible ways of kind of pinching off that T2. That's the last thing we did. So this is it. This is the way that all the 60 CFTs look. By the way, I should point out that the 2,0 theories are, in some sense, very special cases where you just have none of this extra structure and you just have that link by itself. Those things turn out to be all the 2,0 theories. Okay. So what's next? So I mentioned some near-term goals. Here are some near-term goals that are actually in progress and will hopefully appear soon. One is to take all these 6-dimensional theories and see what happens to them when you go down in dimension. So this is, by this point, a rather big industry in the context of the formal study of quantum field theory or the 2,0 theories. But that's a pretty tiny subset of the theories I'm talking about here, right? So you might ask, what's going on when you take this bigger class of theories and start compactifying them down? We're surely going to learn some interesting things about strong coupled dynamics for these field theories in, say, 5 dimensions in this case when we go down in a circle, or in 4 dimensions when we go down on a Riemann surface. Okay, what's the operator content of these theories? Turns out that you can use the F-theory geometry to start pulling out some details about the operator content and also some of the scaling dimensions. And this basically just follows from the fact that you can write down kind of a holomorphic geometry and then use that holomorphy to constrain the structure of the operators. Something I didn't talk about too much, but the fact that you know the lattice of strings, the possible string charges that you can have, it allows you to actually say some interesting things about kind of extended objects that live in these systems. So this is another kind of topic that's been heavily studied in the context of the 2,0 theories. But it's basically a very similar story that you can tell in the context of these 1,0 theories. And hopefully this will be out by the end of the week, although I might be off by some order one number. Okay, so what are the broader goals? So as I was explaining at the beginning, kind of the broader goals are, what are the rules of the game? Namely, take a geometry and start squeezing out effective field theories. What I told you about is kind of one particular example where we can really say something very tight and controlled, and we classify the 6-dimensional superconformal field theories. More general questions. Now that you've got this list, what can you say about them? What can you say about these physical theories? What happens to these theories when they go down in dimension? Another thing I didn't talk about too much is kind of using them for model building in extra sectors. Happy to talk more about that too. Okay, what else can you do? Well, one of the rules of the game that I was basically using was this kind of idea of a pinching donut telling you about geometric sources in the F-theory compactification. Now, in physics terms, we know that point-like sources are kind of just the tip of the iceberg. You might imagine dipole moments, or things that are kind of spread and don't have exactly a point-like object. What do these things correspond to geometrically? Do we know the kind of mathematical definition of these objects? Turns out that it's a pretty subtle object, and basically what you have to do is deform these things into a limit that basically looks like just point sources, and then you take some limit where things start spreading out. This is a pretty tricky subject, and one of the people on this project was a mathematician, and two of them are mathematicians. So that should give you an idea of how heavy it gets. Basically the idea is you have these branes that are intersecting, and you start making things like dipole moments. And these are things that are part of the geometry, but are a little bit tricky to describe just using the methods we got right now. So here's an example of how that fits together. It involves kind of this theory of limiting mixed Hodge structure, in particular the so-called intermediate Jacobian of the hypercubed moduli space, and matching it to kind of a topological field theory over here. So this is just kind of, I know this is fast, but this is kind of like a thing that's taking up a lot of time too. Okay, more broadly, I talked about kind of classical geometry. That's the main thing I focused on here. But you might ask, what's going on? When we start taking the quantum corrections into account? Namely, if you start pushing this beyond kind of the classical regime of the geometry, what happens? I'm almost out of time, I think, so I'm not going to talk too much about it, which is good because I don't have too many concrete things to say. But two things I've been playing with in this context, which I think naturally fit, is basically asking what happens if you make, say, space-time directions non-commutative, or say start decomposing things into bits of information. So I think these are both kind of areas where these are more like speculative directions, but I think it's important to investigate them in tandem because where did this geometry come from? It presumably emerges from some kind of picture like this, but who knows? Okay, so I'm basically going to wrap up now. So what this talk was about was basically about taking the geometry of extra dimensions and squeezing out effective field theories from them. And what I did is I told you about a particular class where it's pretty subtle to describe using kind of the standard techniques from bottom-up perspective how to build a CFT. This is really one of those places where string geometry provides some insights into how to think about these theories. So in particular, I told you about how to classify all the 6D SCFTs. So I think the next thing up is the fact that all of these CFTs kind of had similar structure. They all kind of look the same. They all look like a big quiver with one spine. Means that if you learn a lesson about one of these 60 CFTs, you will have learned a lesson potentially about all of them. So that's I think the next thing up, which is to kind of start extracting universal lessons about these 6-dimensional SCFTs and start pulling things together from that perspective. And of course, along those lines, compactifying to lower dimensional systems. So thanks for your attention, and I'll stop there.
Question? Jack?
Yeah.
It seems like there's a lot of fixed structure to this. Is there any chance of taking, let's suppose the standard model is right with the Higgs boson, and working back up the chain and saying, well, this could only come from this or that structure, if that were scale, if that were the physics up to the gut scale or something like that?
Yeah, so that's part of what I was doing my PhD thesis on, which was kind of the particle physics side of the coin, which was, so in 4 dimensions, things are a little bit looser, and the reason is that instead of talking about six extra dimensions, it becomes an 8-dimensional geometry. And as you add more internal directions, things aren't as constrained. But one of the things you can do to kind of restore that rigidity is ask, well, if the gut scale can be decoupled from the Planck scale, so this is kind of the opposite philosophy than what a lot of string theorists want to say. But numerically, gut scale does not equal Planck scale. So if you take that seriously and look for a limit where the Planck scale actually decouples completely, then you can shove it off to infinity but keep the gut scale around 10 to the 16 Jev, then indeed there is more rigid structure. It's not at the point where you can say, oh, this is the only thing that could happen, but it becomes, a lot of things get kind of pinned down. So it's not a completely loose object, like, if you heard landscape talks, and oh yeah, I could live in a world with pink elephants. And, it's completely loose. It's not as loose in a lot of these limits where you take gravity and you decouple it. So for example, that theta-1,3 calculation was an example of where you kind of force some structure in, say, the CKM matrix calculation, and in turn forces further structure on the neutrino mixing. So that's another example of the kind of thing. But I don't think it's at the level of we're going to classify all the things. So that was more like model building, and there's more options. So, but it does get more rigid.
Any other questions? All right, well, let's thank Jonathan again. So do you want to meet now, or what do you want to do?